So what's up? It's Iverson again, and welcome to another edition of Alan Vlogs. So we are here to discuss the chapter of all summaries that we have discussed in Cisco. So first comes the chapter 1, which is exploring the network. So networks and the internet have changed the way we communicate, learn, work, and even play. Network comes in all sizes. They can range from simple networks consisting of two computers to networks connecting millions of devices. The internet is the largest network in existence. In fact, the term internet means network of networks. The internet provides the service that enable us to connect and communicate with our families, friends, work, and interests. The network infrastructure is the platform that supports the network. It provides the stable and reliable channel over which communication can occur. It is made up of network components including end devices, intermediate devices, and lastly the network media. So networks must be reliable. This means the network must be fault tolerant, scalable, provide quality of service, and ensure security of the information and resources on the network. Network security is an integral part of computer networking, regardless of whether the network is limited to a home environment with a single connection to the internet or as large as a corporation with thousands of users. No single solution can protect the network from the variety of threats that exist. For this reason, security should be implemented in multiple layers, using more than one security solution. The network infrastructure can vary greatly in terms of size, number of users, and number of types of service that are supported. The network infrastructure must grow and adjust to support the way the network is used. The routing and switching platform is the foundation of any network infrastructure. This chapter focused on networking as a primary platform for supporting communication. So the next chapter will introduce you the Cisco Internetwork Operating System or iOS, used to enable routing and switching in a Cisco network environment. So let us go in the next chapter, configure a network operating system. So chapter 2, configure a network operating system. Cisco iOS is a term that encompasses a number of different operating systems which runs on various network devices. The technician can enter thousands to configure or program the device to perform various networking functions. Cisco iOS routers and switches perform functions that network professionals depend upon to make their networks operate as expected. The services provided by the Cisco iOS are accessed during a command line interface or the CLI, which is accessed by either the console port, the AUX port, or through SSH or Telnet. After connected to the CLI, network technicians can make configuration changes to Cisco iOS devices. The Cisco iOS is designed as a modal operating system, which means a network technician must navigate through various hierarchical modes of the iOS. Each mode supports different iOS commands. Cisco iOS routers and switches support a similar modal operating system, support similar command structures, and support many of the same commands. And in addition, both devices have identical initial configuration steps implementing in the network. So the next chapter is the chapter 3, which is network protocols and communications. So in this chapter we have data networks are system of devices, intermediary devices and media connecting them. For communication to occur, these devices must know how to communicate. This device must comply with communication rules and protocols. The TCP or IP is an example of a protocol suite. Most protocols are created by a standards organization such as the IET or the IEEE, and the Institute of Electrical and Electronics Engineers is a professional organization for those in the electrical engineering and electronics fields. So ISO, the International Organization for Standardization, is the world's largest developer of international standards for a wide variety of products and services. The most widely used networking models are OSI and TCP/IP models, associating the protocols that set the rules of data communications within the different layers of these models is useful in determining which devices and services are applied at specific points, such as data passes across the LANs and the WANs. Data that passes down the stack of the OSI model is segmented into pieces and encapsulated with address and other labels. The process is reversed as the pieces are de-encapsulated and passed up the destination protocol stack. The OSI model describes the process of encoding, formatting, segmenting, and encapsulating data for transmission over the network. TCP or IP protocol suite is an open standard protocol that has been endorsed by the networking industry and ratified or approved by a standards organization. The Internet Protocol Suite is a suite for protocols required for transmitting and receiving information using the Internet. So we are here at chapter 4, the network access. So here, the TCP or IP network access layer is the equivalent of the OSI data link layer or the layer 2 and the physical layer, which is the layer 1. The OSI physical layer provides the means to transport the bits that make up a data link layer frame across the network media. The physical components are the electronic hardware devices, media, and other connectors that transmit and carry the signals to represent the bits. Hardware components such as network media, network adapters or NICs, NICs, interface and connectors, cables, cable materials, and cable designs are all specified in standards associated with the physical layer. The physical layer standards address the three functional areas: the physical components, frame encoding technique, and signaling method. Using the proper media is important part of network communications. Without the proper physical connection, either wired or wireless communication between any two devices will not occur. So, let us move on to the next chapter, which is the chapter 5, the Ethernet. So, chapter 5, Ethernet is the most widely used LAN technology today. It is a family of networking technologies that are defined in the IEEE 802.2 and 802.3 standards. Ethernet standards define both the layer 2 protocols and the layer 1 technologies. For the layer 2 protocols, as with all 802 IEEE standards, Ethernet relies on two separate sublayers of data link layer to operate logical link control and the MAC sublayers. At the data link layer, the frame structure is nearly identical for all bandwidths of the Ethernet. The Ethernet frame structure adds headers and trailers around the layer 3 PDU to encapsulate the message being sent. There are two styles of Ethernet framing, the IEEE 802.3 Ethernet standard and the DIX Ethernet standard, which is now referred to the Ethernet 2. The most significant difference between the two standards is the addition of a start frame delimiter or the SFD and the change of the type field to a length field in the 802.3. Ethernet 2 is the Ethernet frame format used in TCP or IP networks. As an implementation of IEEE 802.2 or 802.3 standards, the Ethernet provides MAC addressing and error checking. So let us move to the next chapter. So chapter 6, network layer. The network layer or OSI layer 3 provides the service to allow the end devices to exchange data across the network. To accomplish this end-to-end transport, the network layer uses four basic processes: IP addressing for end devices, encapsulation, routing, and the encapsulation. The Ethernet is largely based on the IPv4, which is still the most widely used network layer protocol. An IPv4 packet contains the IP header and the payload. However, IPv4 has limited number of unique public IP address available. This led to the development of IP version 6 or the IPv6. The IPv6 simplified header offers several advantages over IPv4, including better routing efficiency, simplified extension headers, and capability for per-flow processing. Plus, IPv6 addresses are based on 128-bit hierarchical addressing as opposed to IPv4 with 32 bits. This dramatically increases the number of available IP address. In addition to hierarchical addressing, the network layer is also responsible for routing. Hosts require a local routing table to ensure that packets are directed to correct destination network. The local table of a host typically contains a direct connection, local network route, and local default route. The local default route is the route to the default way. The default gateway is the IP address of a router interface connect to the local network. When a host needs to forward a packet to a destination address that is not on the same network as the host, the packet is sent to the default gateway for further processing. When a router, such as the default gateway, receives packet, it examines the destination IP address to determine the destination network. The routing table of a router stores information about direct connected routes and remote routes to IP networks. If the router has an entry in its routing table for the destination network, the router forwards the packet. If no routing entry exists, the router may forward the packet to its own default route. If one is configured, or it will just drop the packet. So let us move on to the next activity, next chapter, the chapter 6, chapter 7, which is the IP addressing. So here, IP addresses are hierarchical with network, subnetwork, and host portions. An IP address can represent a complete network, a specific host, or the broadcast address of the network. Understanding binary notation is important when determining if two hosts are in the same network. The bits within the network portion of the IP address must be identical for devices that reside in the same network. The subnet mask or prefix is used to determine the network portion of an IP address. IP address can be assigned either statistically or dynamically. DHCP enables the automatic assignment of addressing information such as IP address, subnet mask, default gateway, and other configuration information. IPv4 hosts can communicate on one of three different ways: unicast, broadcast, or multicast. Also, blocks of address that are used in networks that require limited or no internet access are called private addresses. So the private IPv4 addresses blocks are the 10.0.0.0 slash 8, 172.16.0.0 slash 12, and 192.168.0.0 is the slash 16. The depletion of IPv4 address space is the motivating factor for moving to IPv6. Each IPv6 address has 128 bits versus the 32 bits in an IPv4 address. If IPv6 does not use dotted decimal subnet mask notation, the prefix len is used to indicate the network portion of an IPv6 address using the following format: IPv6 slash address len, IPv6 address slash prefix len. So let's move on to the next chapter. It's chapter 8, subnetting IP networks. So the process of segmenting a network by dividing it into multiple smaller network space is called subnetting. Every network address has valid range of host addresses. All devices attached to the same network will have an IPv4 host address for that network with a common subnet mask or network prefix. Traffic can be forwarded between hosts directly if they are on the same subnet. Traffic cannot be forwarded between subnets without the use of a router. To determine that if traffic is local or remote, the router uses subnet mask. The prefix and the subnet mask are different ways of representing the same thing, the network portion of an address. IPv4 subnets are created by using one or more of the host bits as network bits. Two very important factors that will lead to the determination of the IP address block with the subnet mask are the number of subnets required and the maximum number of hosts needed per subnet. There is an inverse relationship between the number of subnets and the number of hosts. The more bits that are borrowed to create subnets, the fewer the host bits that are available. Therefore, there are few hosts per subnet. The formula 2 raised to n, where n is the number of host bits remaining, is used to calculate how many addresses will be available in each subnet. However, the network address and broadcast address within a range are not usable. Therefore, the calculation usable number of addresses, the calculation 2 raised to n minus 2 is required. Subnetting a subnet is or using variable length subnet mask or VLSM was designed to avoid wasting addresses. IPv6 subnetting requires a different approach than IPv4 subnetting. An IPv6 address space is not subnetted to conserve addresses. Rather, it is subnetted to support a hierarchical logical design of the network. So, while IPv4 subnetting is about managing address scarcity, IPv6 subnetting is about building an addressing hierarchy based on the number of routers and the networks they support. So let us move to the next chapter, chapter 9, the transport layer. For the transport layer provides transport-related services by number 1, dividing data received from an application into segments. Number 2, adding a header to identify and manage each segment. Next is using the header information to assemble the segments back into application data. And lastly, passing the assembled data to the correct application. UDP and TCP are common transport layer protocols. UDP datagrams and TCP segments have headers added in front of data that include a source port number and destination port number. These port numbers enable data to be directed to the correct application running on the destination computer. TCP does not pass any data to the network until it knows that the destination is ready to receive it. TCP then manages the flow of data and resends any data segments that are not acknowledged as being received at the destination. TCP uses mechanisms of handshaking, timers, acknowledgement messages, and dynamic windowing to achieve the reliability. The reliability process, however, imposes overhead on the network in terms of much larger segment headers and more network traffic between the source and destination. If the application data needs to be delivered across the network quickly, or if network bandwidth cannot support the overhead of control messages being exchanged between the source and the destination systems, UDP would be the developer's preferred transport layer protocol. UDP provides none of the TCP reliability features. However, this does not necessarily mean that the communication itself is unreliable. There may be mechanisms in the application layer protocols and services that process lost or delayed datagrams if the application has these requirements. So here at chapter 10, which is the application layer. So the application layer is responsible for directly accessing the underlying processes that manage and delivers communication to the human network. This layer serves as the source and destination of the communications across data networks. The application layer applications, services, and protocols enable users to interact with the data network in a way that is meaningful and effective. Applications are computer programs with which the user interacts and which initiate data transfer process that the user requests. Services are background programs that provide the connection between the application layer and the lower layers of the networking model. Protocols provide the structure of agreed upon rules and processes that ensure services running on one particular device can send and receive data from a range of different network devices. The delivery of data over the network can be requested from a server by a client or between devices that operate in a P2P arrangement. In P2P, the client or server relationship is established according to which device is the source and destination at the time. Messages are exchanged between the application layer services at each end device in accordance with the protocol specifications to establish and use these relationships. Protocols like HTTP, for example, support the delivery of web pages into end devices. SMTP and IMAP and POP support sending and receiving email. SMB and FTP enable users to share files, and P2P applications make it easier for consumers to seamlessly share media in distributed fashion. DNS resolves the human legible names used to refer network resources into numeric addresses usable by the network. Clouds are remote upstream locations that store data and host applications so that users do not require as many local resources, and so that users can seamlessly access content on the different devices from any location. All of these elements work together at the application layer. The application layer enables users to work and play over the internet. So let's move on to our last chapter. Chapter 11 is build a small network. So in order to meet user requirements, even small networks require planning and design. Planning ensures that all requirements, cost factors, and deployment options are given due to consideration. The most important part of network design is reliability, scalability, and availability. Supporting and growing a small network requires being familiar with the protocols and network applications running over the network. Protocol analyzers enable the network professional to quickly compile statistical information about the traffic flows of a network, and information gathered by the protocol analyzer is evaluated based on the source and destination of the traffic as well as the type of traffic being sent. This analysis can be used by a network technician to make decisions on how to manage the traffic more efficiently. Common network protocols include DNS, Telnet, SMTP, POP or POP, DHCP, HTTP, and FTP. It is a necessity to consider security threats and vulnerabilities when planning a network implementation. All network devices must be secured. And this includes routers, switches, and end-user devices, and even security devices. Networks need to be protected from malicious software such as viruses, Trojan horses, and worms. Antivirus software can detect most viruses and many Trojan horse applications and prevent them from spreading in the network. The most effective way to mitigate a worm attack is to download security updates from the operating system vendor and patch all vulnerable systems. Networks must also be protected from network attacks. Network attacks can be classified into three major categories: the reconnaissance, access attacks, and denial of services. There are several ways to protect a network from attacks. First, the authentication, authorization, and accounting, or the AAA Network Security Service, provide the primary framework to set up access control on a network device. The AAA is a way to control who is permitted to access a network, authenticate what they can do while they are there, authorize, and to watch the actions they perform while processing the network. Accounting. A firewall is one of the most effective security tools available for protecting internal network users from external threats. A firewall resides between two or more networks and controls the traffic between them, and also helps prevent unauthorized access. To protect network devices, it is important to use strong passwords also when accessing network device remotely. It is highly recommended to enable SSH instead of the unsecured telnet. After the network has been implemented, a network administrator must be able to monitor and maintain the network connectivity. There are several commands available toward this end. For testing the network connectivity to local and remote destinations, commands such as ping, telnet, and traceroute are commonly used. On Cisco OS device, the show version command can be used to verify and troubleshoot some of the basic hardware and software components used during the boot process to view information for all network interfaces on a router. The show IP interface command is used, and the show IP interface brief can also be used to view a more abbreviated output than the show IP interface command. Cisco Discovery Protocol, or CDP, is a Cisco proprietary protocol that runs the data link layer because CTP operates the data link layer. Two or more Cisco network devices, such as the routers that support different network layer protocols, can learn about each other even if layer 3 connectivity does not exist. Cisco iOS configuration files such as startup config or running config should be archived. These files can be saved into a text file or stored on a TFTP server. Some models of routers also have a USB port, and a file can be backed up to a USB drive. If needed, these files can be copied to the router and/or switched from the FTP server or USB drive. So that's all for today's video, and I hope you like it, and I hope you learned a lot, and thank you for watching.